For those who love exploring and observing the bright stars in the night sky, concepts like comets, meteoroids, and asteroids are familiar. They are fragments of matter, wandering through the expanses of space, becoming regular visitors to our solar system and interacting with observable orbits from Earth. Some comets even establish fixed orbits that can be observed periodically. This is where a new issue arises. You may not be aware that all comets and asteroids found today have their origins in the solar system. That's why Oumuamua became special. Oumuamua was first discovered by astronomers in October 2017. It is the first interstellar object to visit our solar system with an unusual orbit. Initial reports about Oumuamua's peculiar characteristics led some to speculate that the object could be an extraterrestrial spacecraft sent from a distant civilization to investigate life within our solar system. However, these claims remain unverified. Therefore, in today's video, we will review the evidence and shed light on the mysteries surrounding this enigmatic object. Is it an extraordinary comet, or part of a mysterious plot from other realms of space? Oumuamua. As the first interstellar object to visit the solar system from another region of space, Oumuamua immediately captured the attention of the scientific community and the general public through various media outlets. Countless hypotheses were formulated based on the object's peculiar characteristics and unclear origin. This included rumors and ambiguous information about extraterrestrial spacecraft. Unlike most other comets, Oumuamua lacked a bright coma or a dust tail. Its peculiar shape, resembling a cigar or a double pancake, and its small size suggested it resembled an asteroid more than a typical comet. However, the puzzling acceleration of Oumuamua away from the Sun, in a manner that astronomers couldn't explain, left scientists bewildered. Some speculated that it could be an extraterrestrial spacecraft. At the University of California, Berkeley, an astronomer and a planetary scientist from Cornell University suggested that the mysterious deviation of the comet from its hyperbolic trajectory around the Sun could be explained by a simple physical mechanism commonly observed in many icy comets: the release of hydrogen gas as the comet heats up under the Sun's radiation. What sets Oumuamua apart from other carefully studied comets in our solar system is its size. It is small to the extent that gravitational forces acting on it are slightly altered by the tiny thrust generated when hydrogen gas escapes from the ice. Most comets are essentially dirty snowballs that periodically approach the Sun from beyond our solar system. When warmed by sunlight, comets release water and other molecules, creating a bright coma or a coma-like region around them, often accompanied by gas and dust tails. The expelled gas acts like a propulsion system on a spacecraft, giving comets a slight kick that changes their trajectory slightly from the typical elliptical orbits of other objects in the solar system, such as asteroids and planets. When discovered, Oumuamua lacked a coma or a tail and was too small and too far from the Sun to release enough energy to produce significant outgassing. This led astronomers to speculate wildly about its composition and what propelled it outward. Was it an iceberg-like block containing hydrogen, releasing hydrogen gas? Or was its nature that of a large, porous snowflake pushed by the gentle pressure of the Sun? A light sail created by an extraterrestrial civilization? A spacecraft, propelled by its own means? Jennifer Bergner, an assistant professor of chemistry at UC Berkeley, specializing in studying chemical reactions occurring on icy surfaces in the frigid vacuum of space, proposed a potentially simpler explanation. She discussed this idea with her colleague, Daryl Seligman, currently a National Science Foundation graduate research fellow at Cornell University, and they decided to collaborate to test it. Essentially, a comet moving through the space between stars will be subjected to cosmic radiation, causing the ice to cook and form hydrogen. Therefore, their hypothesis was, if this happens, could Oumuamua actually trap it within its body so that when it enters the solar system and gets heated, it would release more hydrogen gas? Bergner raised the question, could that produce the force needed to explain the non-gravitational acceleration quantitatively? Surprisingly, she discovered that experimental studies published in the 1970s, 80s, and 90s demonstrated that when ice is bombarded by high-energy particles similar to cosmic rays, a significant amount of hydrogen molecules is created and trapped within the ice. In fact, cosmic rays can penetrate ice for tens of meters, turning a quarter of the water into hydrogen gas. For a comet with a diameter of a few kilometers, the amount of gas escaping would come from a very thin shell compared to the majority of the object. Thus, in terms of structure and considering any acceleration, it is not necessarily an effect that can be detectable. However, because Oumuamua is so small, scientists had to consider that it actually generates enough force to account for this acceleration. Initial studies and images suggested that the mysterious object had a reddish hue, with estimated dimensions falling around 115 c/111 x 19 meters. However, astronomers couldn't be certain about the actual size as it was too small and too far for telescopes to resolve. The size had to be inferred from the brightness of the comet and how it changed as the comet sped away. To date, all comets observed in our solar system, short-period comets originating from the Kuiper Belt, and long-period comets from the more distant Oort cloud, have diameters ranging from about 1 kilometer to hundreds of kilometers. What's particularly unique about Jenny's idea is that it precisely aligns with what would happen to comets between stars. We have all sorts of wild ideas like hydrogen iceberg blocks and other crazy things, and those are just the broadest, most general explanations. Comets. Comets have been mysterious celestial bodies in our solar system for centuries. For a long time, they were viewed as ominous omens, appearing and disappearing, creating a sense of the eerie and even fear. It wasn't until later, with the development of science, that it became known that comets are merely remnants of ice and rock from the formation of the solar system about 4.5 billion years ago. They serve as records of the conditions present during the early stages of our solar system. Comets between stars can also offer clues about the conditions around other stars surrounded by planet-forming disks. They act like snapshots of what our solar system looked like during its evolution, akin to the current protoplanetary disks. Therefore, studying them is a way to look back at how our solar system appeared during its formative stages. Planetary systems in other galaxies also seem to have comets, and some of them might be ejected due to gravitational interactions with other objects in the system, a phenomenon astronomers believe has occurred in the history of our own solar system. Some of these interstellar comets occasionally enter our solar system, providing opportunities to learn about planet formation in other systems. According to Seligman, these comets and asteroids within our solar system have taught us more about planet formation than what we've learned from actual planets within our solar system. He believes that comets between stars may reveal more about planets outside our solar system than the exoplanets we are currently trying to measure. Most comets that we observe today come from distant regions of the solar system, originating in places known as the Kuiper Belt, extending from the orbit of Neptune, and the Oort cloud, forming the outermost part of the solar system. The orbits of comets are highly elliptical, with a center at the Sun and the far end sometimes extending well beyond the orbits of Neptune or Pluto. Occasionally, the orbits of comets will bring them into direct contact with other celestial bodies in our solar system. The gravitational influences of various planets and the Sun shape their orbits, making such collisions more likely as comets make numerous trips around the Sun. As comets approach the hottest source in the solar system, the intense radiation begins to vaporize their gases and ices, creating a bright cloud around the object. Officially known as the comet's coma, this cloud can extend for thousands of kilometers. When we observe comets from Earth, This coma is often what we perceive as the head of the comet. On the other hand, radiation pressure from the sun pushes material away from the comet, forming two tails. The first tail is the dust tail, and the second tail is the gas tail, plasma tail, formed from gases vaporized from the nucleus and energized by interactions with the solar wind. Dust from the tail is left behind like a breadcrumb trail, indicating the path the comet has taken through the solar system. The gas tail is often challenging to see with the naked eye, but a photograph reveals it shining with a bright blue color, extending directly away from the sun and influenced by the solar wind. It typically stretches over a distance equal to the sun's distance to Earth. Based on these characteristics, Oumuamua indeed doesn't resemble a typical comet. Mysteries on Oumuamua. Prior to this, astronomers had published numerous papers on what could be learned from observing any interstellar comets between stars in our solar system. And then came Oumuamua. On October 19, 2017, on the island of Maui, astronomers using the Pan-STARRS 1 telescope operated by the Institute for Astronomy at the University of Hawaii at Manoa first spotted what they thought was a comet or asteroid. Upon realizing its inclined orbit and high speed of 87 km/s, suggesting it originated from outside our solar system, they named it 1I Oumuamua, Hawaiian for a messenger from afar, arriving first. It was the first known interstellar object beyond the dust particles ever seen in our solar system. The second such object is 2I Borisov, discovered in 2019, although it looks and behaves more like a typical comet. As more astronomical observations focused on Oumuamua, astronomers were able to map its orbit and determine that it had swung around the sun and was heading out of the solar system. Due to Oumuamua's periodic and asymmetric changes in brightness, believed to be very elongated and tumbling end over end, astronomers inferred its shape. They also noted a small acceleration away from the sun, larger than typical for asteroids and more characteristic of comets. When regular comets approach the sun, water and gases escaping from their surfaces create a glowing coma and release dust in the process. Typically, the leftover dust from comets is observed as a tail, while the gas and dust pushed by sunlight pressure form a second tail extending away from the sun, along with a bit of inertia carrying it outward. Other compounds, such as trapped organic materials and carbon monoxide, can also be released. However, astronomers couldn't detect a glowing coma, escaping gas molecules or dust around Oumuamua. Additionally, calculations showed that solar energy touching the comet wouldn't be enough to vaporize water or organic compounds from its surface to produce observable gravitational acceleration. Only easily vaporizable gases like hydrogen, nitrogen, or carbon monoxide could provide sufficient acceleration for observable effects based on solar energy. In the history of observing celestial objects in the sky, scientists have never seen a comet in our solar system without a dust coma. Therefore, the observed gravitational acceleration was truly peculiar. This led to various speculations about which easily vaporizable molecules could be present in the comet causing the acceleration. Seligman himself published a paper arguing that if the comet were composed of solid hydrogen, an icy hydrogen iceberg, it would release enough hydrogen under the sun's heat to explain the unusual acceleration. Under suitable conditions, a comet consisting of solid nitrogen or solid carbon monoxide would also release gas with sufficient force to affect the comet's orbit. However, astronomers had to try to explain the conditions that could lead to the formation of solid hydrogen or nitrogen objects, something never observed before. And how could an object composed of solid hydrogen survive for about 100 million years in space between stars? Bergner believes that the release of trapped hydrogen gas within the ice could be sufficient to accelerate Oumuamua. As both an experimentalist and a theorist, she researched the interaction of extremely cold ice, cooled to 5 or 10 degrees Kelvin, the temperature of the interstellar medium, ISM, with energetic particles and radiation found in the ISM. In her search through previous publications, she found many experiments demonstrating that high-energy electrons, protons, and heavier atoms can convert ice into hydrogen molecules, and the soft snowball structure of comets can trap gas within bubbles inside the ice. Experiments show that when heated, for example, by the sun's warmth, ice sublimates, transitioning from an amorphous structure to a crystalline structure, and pushes the bubbles out, releasing hydrogen gas. The ice on the surface of a comet, Bergner and Seligman calculated, could release enough gas in the form of straight jets or fan-shaped sprays to affect the orbit of a small comet like Oumuamua. The main takeaway is that Oumuamua fits the profile of a comet between stars that has undergone extensive processing. The models we ran match what we see in the solar system from comets and asteroids. So, essentially, we can start with something that looks like a comet and run this scenario. This idea also explains the lack of a dust coma. Dark comet. Seligman states that their conclusions regarding the acceleration source of Oumuamua will conclude the book on comets. Since 2017, he, Bergner, and their colleagues have identified 6 other small comets without observable comas, but with small gravitational accelerations, indicating that such dark comets are common. Along with Oumuamua, they reveal that there is much to learn about the nature of small objects in the solar system. One of these dark comets, 1998 KY26, is the next target for Japan's Hayabusa 2 mission, tasked with collecting samples from the asteroid Ryugu. 1998 KY26 was initially thought to be an asteroid until it was identified as a dark comet in December. Jenny might have been correct about the retained amount of hydro. We have never considered that possibility in previous studies and reports. Amidst the discovery of other dark comets in the solar system and Jenny's brilliant idea, I think it must be accurate. Water is the most common component of comets in the solar system and possibly in systems beyond. If you place a water-rich comet into the Oort cloud or launch it into the interstellar environment, you will get a shapeless ice containing hydrogen. This condition will form in any ice-rich body exposed to high-energy radiation. So researchers suspect that a similar mechanism will occur in comets approaching the Sun from the Oort cloud in the outer region of the solar system, where comets are irradiated by cosmic rays, similar to comets between stars. Future observations of hydrogen gas escaping from long-period comets can be used to test the formation and trapping scenario of hydrogen. Many more dark and interstellar comets will be discovered by the Large Synoptic Survey Telescope, LSST, of the Vera C. Rubin Observatory, allowing astronomers to determine the prevalence of hydrogen gas escaping from comets. Seligman has calculated that the survey will take place at the Vera C. Rubin Observatory in Chile and is expected to commence operations in early 2025. Aiming to detect 1 to 3 comets between stars like Oumuamua each year, with the possibility of finding many more comets. Theories about spaceships. Returning to the question of whether Oumuamua is a spacecraft or not, the idea of it being an interstellar spaceship is understandable, given that we have never seen an object like it between stars before. Alongside scientific research reports attempting to explain the peculiar characteristics of Oumuamua, there are also speculative reports suggesting that it could be an artificial object from an extraterrestrial civilization. A recent paper from researchers at the Harvard-Smithsonian Center for Astrophysics has raised the possibility of the dark red elongated object, 10 times longer than it is wide, moving at a speed of 196,000 miles per hour, being of artificial origin. The paper is authored by Abraham Loeb, a professor and chair of astronomy, and Shmuel Bialy, a postdoctoral scholar at the Harvard-Smithsonian Center for Astrophysics. Loeb has published over 700 papers and 4 books on topics such as black holes, the future of the universe, the search for extraterrestrial life, and the first stars. In the paper submitted to the Astrophysical Journal, Loeb suggests that Oumuamua could be a fully operational probe intentionally sent near Earth by an extraterrestrial civilization. Loeb argues, considering an artificial origin, one possibility is that Oumuamua is a light sail floating in interstellar space as a debris from advanced technological equipment, suggesting that this object could be propelled by solar radiation. The article points out that there are similar light sails existing on Earth. Light sails of comparable size have been designed and manufactured by our civilization, including projects like Icaros and the Starshot Initiative. Light sail technology could be widely used for transporting cargo between planets or between stars. This explains the various anomalies of Oumuamua, such as its unusual shape inferred from its light curve, low thermal emission indicating high reflectivity, and its non-gravitational acceleration without any signs of a comet-like tail or spin-up. Loeb wrote in an email that, "It is exciting to live at a time when we have the scientific technology to search for evidence of civilizations beyond Earth. The evidence for Oumuamua being an artificial object is not persuasive but interesting. I will be truly excited when we have persuasive evidence." In the paper, the duo hypothesizes that the high speed and unusual trajectory of the object could result from it no longer being operational. Oumuamua looks like an asteroid or comet, whereas the spectral data of a solar sail would appear quite different. The new paper suggests that the sail has been covered with a layer of interstellar dust, obscuring its actual spectral signature. Any functioning spacecraft is almost certain to retract its solar sail when in interstellar space to avoid damage. The sail would be useless when far away from a star, so there's no reason for it to be deployed. If it were to be deployed upon entering the solar system, it would be in a pristine state. Even if it were opened, dust would still accumulate primarily on the front, similar to bugs on a windshield. Oumuamua also moves in a complex tumbling motion, but a functioning solar sail would have a much smoother path and a clearly observable acceleration due to radiation pressure, according to Jackson. He explains that even the tumbling motion of a solar sail would be affected by much stronger radiation pressure than what is observed. He also notes that a solar sail would be thinner than described by the authors of the new paper. The solar sail also cannot change its direction after being launched. So if Oumuamua is indeed a solar sail, it would be traceable back to its origin. Up until now, there is no clear origin for Oumuamua. Additionally, tracking becomes challenging due to the motion of stars, and any assumed extraterrestrial civilization would face the same issue when plotting such a long trajectory from the start, aside from the debate on whether they would want to send a probe that they know wouldn't reach its destination for millions of years. Regarding Oumuamua, there is little evidence because astronomers couldn't observe it for long, opening up possibilities for speculative claims in the name of science. Nevertheless, the future with more advanced observational and tracking instruments will bring more answers to humanity. We will all be watching and waiting for the upcoming discoveries.